Hi everyone. We are going to continue our discussion on isomers, in particular stereoisomers. In the previous video, we've taken care of constitutional isomers, at least for now. That was video 02C50. And we looked at like a decision tree. Like if we have two molecules, A and B, that have the same molecular formula, are they identical? Constitutional isomers, enantiomers, and diastereomers. Those are the four choices, or none of the above. And we're going to continue our discussion, in particularly with enantiomers, deciding whether a molecule is chiral or achiral. A molecule has to be one of those two, and this new term, chiral center. Okay, like I mentioned before, we were looking at specific molecules that are chiral and achiral in the previous video. So that previous video was 02C50. So in 02C50, let me just double check. We saw two molecules. One of the molecules was this, OH, and the other molecule was the same carbon pattern, but now we switched the OH group from wedge to dash. And we had determined that they are not identical. They are not constitutional isomers because they have the same connectivity. They are stereoisomers. Specifically, enantiomers. And remember, the definition for enantiomers is non-superimposable mirror images. Now, they don't look like mirror images, right? The way that I drew it, they don't look like mirror images. So if I gave you a problem like this, prove to me that you can draw the enantiomer of this molecule. So here's a question mark. What is its enantiomer? Okay. Now, before we do that, before we learn how to draw the enantiomer quickly, because these are enantiomers, just like my hands, and remember that term chiral? Chiral describes an object, whether its mirror image is superimposable or not. And I said that my left hand is chiral, my right hand is chiral also, and they are mirror images, non-superimposable mirror images of each other. So you'll be asked, is a molecule chiral or achiral? So each of these molecules on their own are both chiral. If a molecule is chiral, an enantiomer exists for it. Okay, we're going to look at achiral. I think in this video, right? We saw that a pen cap was achiral because it is superimposable. Here's the mirror image, and it is superimposable on its mirror image. Well, whereas my hands are not superimposable. Okay, so how do I draw the enantiomer? Just draw the mirror image. Okay, so the mirror image looks like this. If I had a mirror right there, you gotta pretend. What do you see if there's a small mirror right here? What would you see? Okay, go ahead and draw that. Pause the video. Draw the mirror image of this. Okay, so I would draw the mirror image like this. You start out here. Okay, so those two carbons mirror each other. Those two, those two, those two. Right? And then, literally, when you look at the mirror, you see a wedge. Okay, so don't automatically draw this as a dash. Okay, you literally see a wedge, and you have an O here. But also, that H is closer to the mirror, so this H is closer to the mirror. It doesn't matter whether you drew the H on the left or right, but I'm really trying to draw exactly what I would see in the mirror. So these two are enantiomers, E. Well, if these two are enantiomers, and these two are enantiomers, what do we say about these two? These two are identical, right? I mean, they literally are the same molecule, on paper also. And now these two are identical. Now, can you see that? Because all you have to do is take this molecule, let's say this molecule is this object here, and just turn it over. When you turn this molecule over, do you see how this carbon that's going up will be now on the right-hand side? And if you think about it, if you have, for instance, my hand here has this red pen away from us. This is a horrible, oops. Okay. This pen is pointing away from us. See, it's behind my hand. So when I turn my hand over, my dash pen now becomes a wedge pen. Just like I have here. The dash turns into wedge. Okay. Now, what is going on? Sorry about that. Okay. What about this molecule? This was the last molecule. Uh-oh. Doesn't want to cooperate. Just give me 1 sec. Okay. Ah, there we go. Let me focus this. Okay, it's going to disappear for a sec. I have to reboot the camera. The last molecule that I showed in the previous video, O2C50, was this. And my question was, well, is it chiral or achiral? Okay. Oh, actually, the question was, given these two molecules, are those two molecules identical, constitutional isomers, enantiomers, or diastereomers? I know we haven't talked a lot about diastereomers. Okay. Diastereomers are stereoisomers that are not mirror images, but we're not going to see many diastereomers until a little bit later. So just like you have this question here, what's the relationship between these two? They are enantiomers. Okay. And when I flipped one over, I could tell that they're mirror images. What about this? You know, the first thing to decide is whether they're constitutional isomers, because if they have the same connectivity, they're not constitutional isomers, so this is X. Okay. Well, if you take this molecule and you turn it over, look what we get here. Interesting, because when we turn it over, we make that OH group a wedge, and now what do you think about these two molecules? They're identical. That's kind of strange. If you're trying to memorize what would happen with this case, because when we turned over this molecule, we got the mirror image, and they're not identical. When we turned this one over, we got the mirror image of the original, and they're not identical. But when we turn this one over, yeah, we get the mirror image, but also they are identical. So these are identical, these two are identical, okay, but these two are enantiomers. So let me just draw you the flowchart one more time, and then we are going to look at another example of enantiomers, and depending on the time, yeah, we'll have time to figure out quickly whether something is chiral or achiral. Oh, by the way, I know I'm going back and forth because I want to really, I'm repeating this to make sure that or eventually will get automatic. These are enantiomers. They are non-superimposable mirror images. They don't look like mirror images until I turn one over, but still, it doesn't matter. You could do whatever you want to this. You could turn it over, you could rotate, you just can't break any bonds. Both molecules are considered chiral, right? A chiral molecule is a molecule that's mirror image is not superimposable. My question is then, are these two chiral? Well, if I drew the mirror image, which is right down here, and they are superimposable, that's not the definition of chiral, that's the definition of achiral. They are not chiral. They are not chiral. Each of these are not chiral. Okay? The mirror images are identical. Okay? So again, remember you have to make sure that they have the same molecular formula. And then you can decide whether they are identical or superimposable, another fancy word for identical. Constitutional isomer, remember the definition, different connections, different connectivity. And if it's not either those two, then they have to be stereoisomers. The stereoisomers can be split into two categories, enantiomers, stereoisomers that are mirror images, my hands. And in this video, I'm still not going to show you an example of diastereomers because there's actually very few relative to the other three categories examples of a pair of diastereomers. So again, this will be later, other videos. Before we look at some tricks, ultimately I want to know a trick to figure out whether one molecule is achiral or chiral. Okay. My hand is chiral, my pen cap is achiral. So maybe you have an idea, well, what's the main fundamental difference between my left hand, which is chiral, and this pen cap, which is achiral? But before we do that, I really wanted to discuss just briefly why do I have on these slides for Unit 2 this image here. This is bubblegum, spearmint. These are caraway seeds. The reason why I have this image is because the molecule responsible for the odor and the flavor of those two items, those two molecules are non-superimposable mirror images. What is that the definition of? Non-superimposable mirror images, they are enantiomers. If they are enantiomers, they are mirror images of each other. And not only are they mirror images of each other, they are not identical. So let me show you spearmint. I think I'm going to draw spearmint first. Let me double check. Thanks. Yep, spearmint. And then I want you to draw Carvone. Oh, not Carvone. Caraway seeds. Right? Caraway seeds? I say Carvone because that's the technical scientific name for each of these. But we have spearmint and caraway. The flavoring. So spearmint looks like this. Now, when in doubt, you could always make a model, but it would be good, well, eventually you should be able to do this without making a model. And right now, you won't be able to do this unless you read the textbook very carefully. This is called R. Don't worry about what the R means just yet. We will learn that in probably the next video. But this is spearmint. See, caraway seed is called S-Carvone, and it is the enantiomer of spearmint. Enantiomer. So my question is, how would you draw the enantiomer? Okay. How would you draw caraway? The thing about this molecule, though, is you want to realize that when you have a pi bond, the geometry of those atoms around this pi bond is flat. So there is no, see this methyl group here, there is no wedge and dash. So what happens when you have something that's flat? When you have something that's flat like this, okay, when I turn it over, that connection is still flat. We don't have wedges and dashes. The wedges and dashes that I see are here. Okay. So to draw the enantiomer, there's two ways. Either, and they will look different on paper, but they will be the same molecule. Either draw mirror image, or switch. We're going to call this stereochemistry because we have a wedge and a dash. Switch. I know that this is a new term or a different way of you've seen this word used. Switch to stereochemistry. You know, this whole unit actually is stereochemistry, which is the concepts of chirality, handedness, achiral, enantiomers, all of that. That's all part of the orientation or the stereochemistry of groups around certain carbons. I know I'm being a little bit nebulous, but I want to save some definitions for later. Don't worry about this word. If you want to draw the mirror image, though, draw a little dotted line and literally draw the mirror of this. So you have, oh, why don't you do this at home? Pause the video and draw the mirror image of this. And then when you come back, I'll show you what my mirror image looks like, and then what does this mean by switching stereochemistry, and whether those two things give us the same result. Pause the video. Okay. Welcome back. We will draw the mirror image of this. I have a ring. See, this double bond, if there was a mirror right there, that double bond would show up in the image over there, and this would be like that. Do you see how this double bond oxygen is off away from the mirror? Okay, I'll do that. And that wedge, literally, if you had a mirror right here, it would still look wedge. Okay. See, that's, I fear, is the common mistake. When people are drawing enantiomers, by drawing the mirror image, you don't change this, because you literally see this in the mirror. And here's the H, closer to the mirror, just like this H, and its dash. Okay. That is S. Carvone or Caraway. What I mean by switch stereochemistry is you copy everything exact. You copy everything exact except for the wedge and dash. So do you notice that my drawing, when I do it this method, see, my double bond is still on the right. Just like here, I'm not drawing the mirror image. I'm just drawing this exactly, but switching these two groups. So we have that. And now this is where I change from an R to an S. Again, I'm saving those definitions for a different video. But you're going to change this into a dash, and it actually doesn't matter. And change this to a wedge, and make sure you put the H. It doesn't matter if your wedge is to the left or to the right, because wedge means towards us. So it just depends on what angle you're looking at it, but it's still the same molecule. Right? Still the same molecule. Okay. So both of these are the enantiomer of this. What does that mean? It means that these two have to be identical, because every chiral molecule only has one enantiomer. So these two are identical. And then if these two are enantiomers, these two are also enantiomers. But since every chiral molecule only has one enantiomer, only has one mirror image, right? You can only have one mirror image. So if these two are enantiomers of this, these two have to be identical. Do this in your head. Take this molecule and just turn it over. When you turn it over, that oxygen now is on the left, the double bond is now on the right, and the wedge now looks dash. It's the same molecule, all you had to do was turn it over. So that's why I have that picture on our Unit 2 slides. Okay, they are enantiomers of each other. Alright, let me show you now ways to figure out chiral and achiral. Because, again, if a molecule is chiral, actually I think I'll write this down, because this is a good thing to know. Okay, both of these are chiral. This is chiral also. If molecule is chiral, what do we know about it? It has an enantiomer. It has a non-superimposable mirror image. If it is achiral, its mirror image is, well, here we go. Mirror images that are identical to each other. So if it is achiral, the mirror image is actually identical. That's one way to decide whether something's chiral or achiral. Can you draw the mirror image and tell whether it's identical or not identical? Okay. So ways to tell chiral or achiral. First way, draw mirror image. Is it identical or not? If it's identical, it's achiral. Second way, you don't have to do all of these ways to figure out if it's chiral or achiral. Just pick the one that will tell you the answer the fastest. So if you can draw the mirror image pretty fast, like these two here, and they are not identical, and you could tell that they're not identical, then they are enantiomers. See, if I draw the mirror image of this, you see that I would get this molecule, and they are perfectly identical. When I draw the mirror image of this, and I draw the mirror image, they are not identical. They are not superimposable. So that's one way, draw the mirror image. Second, here's the trick. If it has a plane of symmetry. We have not talked about this trick just yet. Okay. It's a trick. It's achiral. Huh. Alright. Take a look at this molecule of the alcohol. I'm going to go back to our molecule here, and that looks like this. See, the OH is towards you. Is there a plane of symmetry? If I take, let me take a playing card. I'm not drawing the mirror image in this case. I'm looking for a way to cut the molecule in half and that both halves mirror each other. So if I cut it down here, and you're allowed to cut the middle of an atom, do you see how the left and right do not match? Interesting. So there's no plane of symmetry yet. I haven't found one. If I do this, okay, I try to line everything up. You're allowed to twist the molecule in order to find any plane of symmetry. Well, man, almost, I guess. You could cut it down here, but see, the red atom is on the right, so the right side does not mirror the left side. When you don't have a plane of symmetry, you are chiral. You are chiral. Okay. Well, fine. I could not find a plane of symmetry for that organic molecule. Is it true that I could find a plane of symmetry for maybe this molecule? Because I couldn't find one for this molecule. Okay. Take a look at this. Let me make that molecule. Oh, you see what happens when I remove that carbon and I only have now 3 carbons? Well, okay. If I hold it like this, no. If I hold it like this, and I take my playing card, no. We don't have a plane of symmetry that way. But, take it. What if I hold it like this? Again, you're allowed to cut the atom in half, and I'm purposely putting that hydrogen straight up. Okay, you know you could twist this hydrogen to the left or to the right, but if I put it straight up, all of a sudden, now we have a plane of symmetry. Now we have a plane of symmetry. The left side mirrors the right side. That did not happen when I have something like this, because that trick was I cut it down this center. See, this, we have an alpha group to the left. But if I got rid of this alpha group on the left, now I have a plane of symmetry. My hand has no plane of symmetry. Even if I hold my hand like this, and I cut it down this way, there's a palm on the right and the back of my hand on the left. And then the last idea. Remember this object here? Achiral. Because the mirror image is identical. Look at the plane of symmetry. Hold it like this, and put the plane right there. Left mirrors the right. Okay. I know I went through that kind of fast, but let me get this down in words. If it has a plane of symmetry, if you can identify somewhere that it has a plane of symmetry, it is achiral. If no plane of symmetry, chiral. Now the thing about this trick is that you gotta, in your mind or on the model, you have to twist the molecule to check every or a lot of different perspectives. Okay, so we said that this one did not have a plane of symmetry going down this way. Okay, but you know, even if I twist this, okay, no plane of symmetry. Even if I look down this way, no plane of symmetry because the red is on the right. Okay, so that's the second way. You will pick the way that's most convenient for you. So if you can draw a mirror image quickly, then great. See, this one, it's a little bit time consuming. Okay, you have to draw the mirror image and then lift it off the page and see if they're identical or not. So for that one, well, even draw the mirror image, right? That's first way. But even the second way, like, is there a plane of symmetry here? You know, I know that these double bonds make the molecule flat. So I can have a plane of symmetry cutting this way, the plane of the paper. But it's this part here that's not symmetrical from one half to the next. Okay. So let me tell you the third way. The third way is, I don't know. I use this third way the most, and it has a what's called a chiral carbon, or chiral. It doesn't necessarily have to be carbon. It's a chiral center. So chiral center is this. It's a tetrahedral carbon with, and I'm going to use the word paths, 4 different paths. The textbook says 4 different groups. I like to use the word path because, remember, this molecule is chiral. Okay. If it has a chiral center, then the molecule is chiral. For most cases. I got to put a disclaimer here. We're going to see a couple of exceptions, but for now, no exceptions. I'm running out of time. I'm hitting the 30-minute mark, but this molecule here, when I say paths, you stand at this carbon, 4 people, and you tell each person to walk 1 atom away. We have 4 different groups. We have a methyl group on the right, ethyl on the left, OH on the towards us and H away from us. That's 4 different paths. That carbon is called a chiral center, and if it has, let's say, 1 chiral center for now, okay, and then we can get rid of this exception. If it has 1 chiral center, the molecule is chiral. Those are the 3 ways to tell whether a molecule is chiral. In the next video, we'll do some practice, okay, especially this one, because this is the one that we need to know to assign this R and S. We are going to learn how to assign R and S for these chiral molecules.